So we're going to walk through a small example of hashing some objects into a table using open addressing with linear probing. And then we'll also briefly look at separate chaining. So this is a pretty small artificial example, but it'll just give you a sense of how to use that approach to hashing. So here we have a hash table of size 5. So it's got spaces 0 through 4, and each one is currently empty, or you could think about it as null. And then we have a couple of objects. Our objects are classes, so courses, and each course has a course or a section ID. Okay, so we've got a number and we've got a title, and these are the objects we're going to be putting into our table. Now we're going to use a very, very simple hash function. So we're just going to use the hash function of the last digit of the course ID mod the table size. So again, this is a very small example. This is a very simple hash code, but it'll just give you a sense of how things work. So let's take our first object here, the course software engineering with the ID 34015. And again, our hash code is the last digit, which is 5, mod the table size, which is 5. So the value of that is 0. So we're going to go ahead and put software engineering right in position 0. So this position is no longer null or empty. It holds software engineering. Okay, so next up, let's take intro to Unix. So the last digit here is a 1. 1 mod 5 is going to be 1. So we're going to go ahead and put intro to Unix into position 1, which is again no longer null or empty. Okay, next up we're going to add advanced programming. The last digit is a 0. 0 mod 5 is 0. So I go to put this in the 0 position, but because I'm using open addressing or closed buckets, I can't have two objects in the same space. So this can't go here. So because I'm using linear probing, what I need to do is I need to check the next space. But when I check the next space, it's full too. So I can't put advanced programming there either. So I need to go one step further and I need to put it here. So now space 2 is no longer null or empty, and it holds advanced programming. So then I'll come in and I want to put data structure somewhere. The last digit of the code is a 1. 1 mod 5 is a 1. So the hash code for this object is 1. But I go to position 1 and it's already full. So I check position 2, already full. So I need to put this in position 3, which is again now no longer empty or null. And last up, I've got intro to programming. Last digit is a 5. 5 mod 5 is 0. So I go to put this in position 0, it's full. I check 1, it's full. I check 2, it's full. I check 3, it's full. And I end up putting this in position 4. Okay, so now my hash table is full. If I wanted to add another element, I would need to create a larger hash table and I would need to rehash all of my objects. So because the hash code is dependent on the hash table, if I now have a bigger table, the hash code is going to be different. So I would need to rehash all of my objects. Now, what happens if I want to search for, let's say someone else comes up and says, hey, I have this course. I want to know if it's in your table. Database administration. Well, if I want to search for an object, what I do is I find the hash code and then I check that position. So I'd say, okay, let me see, the hash code for this object would be a 2. So let me check 2. Well, that's not the item you're looking for. This is not database administration. But I can't stop there because let's take another example. Let's say someone had asked us to find the course data structures. Okay, if that was the case, we would have checked position 1 and it wouldn't be there. But if we'd stopped looking, we would miss the fact that it actually is in the hash table. So when you're using this kind of approach to resolving collisions, you need to keep on looking until you either hit a space that indicates you can stop, or until you've searched the whole table. So in order to look for database administration, I'd start again at position 2 and I'd check that and it's not a match. But then I would just move forward in the same linear approach and I'd check position 3, not a match, position 4, not a match, position 0, not a match, position 1, not a match. And then I'd wrap back around to where I started, and now I know for a fact that this object is not in my table. If I were to search for data structures, here again my hash code is 1, so I'd check 1, it's not there, that's not a match. I'd check 2, that's not a match. I'd check 3, and that is a match. So here I find my object in the table, and it took me 1, 2, 3 seeks to do so. Okay? Now, what happens if I choose that I want to remove data structures, or let's remove advanced programming from my table. So let's say I've decided to drop this from my hash table for whatever reason. So I get rid of it from my table. But what would happen if I put this back to empty or null? Well, let's say now someone is looking for intro to programming. So someone says, hey, is this course in the table? Well, what we do is we look at the hash code and check that position first, and if it's not a match, we keep looking. So we'd check position 0, intro to programming, that's not a match. We would check, so we'd move on to check position 1, not a match, and then we'd reach an empty space, and if we stopped looking there, we would miss the fact that it really is in the table. But if we keep looking through all the empties, let's say we had a much bigger table that held, 97 or whatever spaces, we don't want to have to check all the empties if we don't have to. So we need some way to differentiate between a position that has never been filled and a position that was once filled but is now empty, meaning you have to keep on looking past it. And we usually use available to indicate that. So this means, hey, there used to be something here, which means there could be matches for what you're looking for beyond this spot. In other words, you got to keep looking. And now we know if we hit an empty, we can just, or null, we can just stop. But if we hit an available, we got to keep looking. So in the example again where I'm looking for intro to programming, I start at position 0, it's not there. I check 1, it's not there. I check 2, there's nothing there, but it's marked as available. That means I need to keep looking. Check 3, it's there. Check 4, there it is, and I find it. And it took me 1, 2, 3, 4, 5 seeks to do so. Now obviously it's taking me a lot of seeks to find things because it's a really small hash table and I've got a lot of clustering and a lot of collisions going on. So this isn't, again, a very realistic example, but it's just an example to kind of show you how the linear probing works. Now let's actually say for a minute, let's go back to having our empty table just again so you can see why we need these two different states of empty or null and versus available. So let's again go back to our empty null. Okay, so let's say again we had first put in software engineering this time, so we put that into position 0. And then we put in intro to programming. That also the hash code is 0, but 0 is full, so we'd put that in position 1. Okay, and now let's say someone wants to find the course advanced programming. So if someone wants to know if advanced programming is in our table, the hash code is going to be 0. We'd check 0, it's not there. We'd check 1, and it's not there. But if we kept on checking, we don't need to check anymore, right? Because there's no chance that advanced programming is anywhere else in my table because there's not been any more entries. But if we didn't have this distinction between available and empty, we'd have to check all of these empties and wrap back around in order to know we could stop. And again, on the hash table of size 5, that's not a big deal, but on a more realistic, larger hash table, you don't want to do that. So that's why you do need those two states to differentiate between, well, there's never been anything here, which means the item you're looking for can't be beyond this position, right? Because of linear probing, if it got bumped up, it would have to have crossed this point at some point. It couldn't go beyond this without crossing this one first. So if you have an empty, meaning nothing's ever been there, then you know that element isn't in the table. But if you were to have the code of available, it means you got to keep looking because at one point there was an element here, which means the entry you're looking for could be further into the table. Okay, so that's just a real quick example of open addressing. So let's look at how this would be a little bit different if we use separate chaining. So separate chaining again allows us to put multiple elements into each position using a linked list. So what that would look like is that let's add advanced programming into the 0 position. Okay, that's the hash code. So now let's say we want to add intro to programming. Again, the hash code is 0. So here we go to position 0, but it's taken, but we can still put something there. So we would just create a list, a linked list, and we now have two we have two objects in that bucket. Okay. And you're just going to have to pretend that arrow is there because I can't get it to work. Okay, so we've got a list of 2 items in that bucket. Next up, database administration, hash code of 2. So we just put that in the 2 position. Next up, software engineering, hash code of 0. We check 0, it's full, but that's okay. We just put it in the list. Okay, so this is what separate chaining looks like. You can still have these collisions, but instead of moving forward with linear probing, you just add it to the list in that particular index of the table. And then if you want to find something, so let's say now someone wants to know if intro to programming is in our table, we take the same approach. We go to that hash code, so position 0 for example, and now we just have to iterate down the list. So we'd say, okay, this is the hash position. Is this the object? No. Is this the object? Yes. So we found it. If we were looking for a different object, we would just, once we reach the end of the list, if we haven't found it in that position, then we're done. We don't need to check any other positions in the table. And if we go to find an object like this one here with a hash code of 1 and we just get an empty position, then we're done. We don't have to keep checking anywhere else. So when we're using separate chaining, we can just use empty. We don't need those 2 states of empty or available. Those are only necessary with linear probing. With separate chaining, just 1 state of empty is enough. Okay, so that's a short little example of tracing the 2 different methods for resolving, or 2 of the available methods for resolving collisions.